Good morning everyone, welcome back to my channel. My name is Marina. I have a master's degree in nautical science and you are watching Celestial Navigation live lectures, making of the textbook part 2. Part 1 is available on my channel under the video selection. If you have any questions you can ask them in the comments on the right, and I will start with the lecture. So as I did yesterday, I'm continuing with today. I already copy-paste just now some data I'm going to use from the yesterday section we did. So we did known star, procedure for known star and known planet, and today we have sun. And because when you are observing stars and when you're observing any celestial object at night, you are limited because you can only do that if you have a clear horizon, and at night time, unless you have moonshine, you are limited to exact moment of astronomical sunset and astronomical sunrise. Those two times are the only times when you can actually make celestial observation. But during the daytime, if you have clear sky, you can observe sun at any moment. So that is why we have a lot of options for daytime celestial navigation. We do have only one object on the sky available, but because of the availability of a horizon, we can observe that same sun in different situations, different positions. So position number 1 is sun at any moment. So anytime when we see the sun and we have a horizon, we can observe the sun. Then we have sun at noon. That is the moment when sun is crossing our meridian, when it is exactly on our meridian. And we have sun at sunrise and sunset. So in the moment of sunrise and sunset. So those are 3 options usually used when it comes to sun and celestial navigation. And let me just check on my channel, can I be heard so I don't talk pointlessly. So let me check my video, my channel. It says I'm alive. Yes, I can hear myself. Yes, I can hear myself. Okay, that's enough. That's enough of that. So audio is good, video is good, video is rolling, you can see me, the quality is 1080p, so everything is peachy. Okay, let's go back to this one, Okay, so celestial navigation, sun at any moment. So observer is observing sun lower limb. Why lower limb? Because we have 2 options. Sun is a very close star to us, and because of that, when we are looking at sun through sextant, we actually see a little ball. Everything else is a tiny dot except moon, of course. So sun and moon are balls, and because they are balls, we're not going to just average guess where is the middle of that ball. What we actually do is we either measure the lower limb of the sun or upper limb of the sun. So usually the most common thing is to measure the lower limb. So in 99.9% of exam questions you will have a lower limb. So let's see the date. The date is, I copy-pasted this from the start, so just I can utilize the text, but the date is actually 23 of April 2008. Now if you have Nautical Almanac for 2008 you can use this one, but you can also, let's switch to this one. Is it this one? Okay, so you can, let me zoom this up a little bit, like this, and what is this? Let's show this. Okay, so the almanac I'm using, it can also be this one, so Nautical Almanac, that you can purchase here. It's a specific Nautical Almanac for education, so all the data I'm using for this textbook is taken from Nautical Almanac for education. Okay, so let's go back to this. So it's 23 of April 2008 and the assumed position is 46 degrees 17.6 north, and longitude is 5 degrees 30.9 west, 30.9 minutes west. And also let me do this so you have a better vision of what I'm doing. Let me see, is the screen matching? Yeah, shut up and go live. Let me refresh the page. Okay, perfect, it's better now. Let's go back to live. Okay, so observer is observing sun lower limb 23 of April 2008, or if you have this almanac you can use that one. If you don't, then you use my educational almanac. Ship's chronometer error is -1 minute 0.6 seconds. The device error, index error of sextant is -0.6. Air temperature is 16, but the pressure is 1005 hectopascals. Time of observation is chronometer time, and it's 10 o'clock in the morning, 09 and 40 seconds. And height observed of the sun is 46 degrees 22.4. So let me see, do I have all the data? I have latitude, longitude, I have ship's chronometer, height of eye. Height of eye is not 16, it's actually 14. So it's 14 minus 06, time and height. Okay, so I have everything. I have all the data, and this that you see right now on the screen is something that you would get on your exam. Now, the temperature and pressure could not be included in case they are not requiring you to make the correction for the height for the air temperature and pressure. So these two could be missing. Also, index error. They could also say that the sextant doesn't have sextant error. So in case you do not have these three values given to you in the exam, then that just means that you skip. You don't read this error, you don't read this error, and you don't need this error. So you don't read three errors from the tables. You just have the dip error because of the height of the eye of the observer. Okay. So the first step is, as always, finding the correct time and date. So the time for us is 10:09:40. Our chronometer error is -1 minute 6, and in calculator we can use calculator, as I explained yesterday. We can use calculator to calculate time. So 10 hours 9 minutes 40 seconds minus 0 hours 1 minute and 6 seconds gives us the correct observation time is 10:08:34. 10:08:34, and the date is the same, so we didn't cross midnight. Our longitude is within zero time zone, so it stays at 23:04/2008. So the second step after we have the correct UT time and date is find the correct date page in Almanac. At this moment you would open your Almanac and look for 23 of April. So let me do that. Let me find let let me find the almanach. 23, 23, 23, 23. Why is it? 23. This is easy when you have book actually in front of you. So let me open it. It has 400 pages, so it takes time to find the exact date. 23 of April, and each page, remember that each page has 3 dates. So once you find the exact page, you also need to look for exact date. So I'm March, no, I need 80. I need April 23, April 23, okay, and I'm looking, let me show you now. Okay, so April 23, and I'm looking at the page where we have sun. So on this page, the first date is 21, so I need to go down. Second date is 22, and the third date on the page is actually 23, so it was Wednesday. And I'm looking at 10 o'clock. So at 10 o'clock, the Greenwich hour angle of sun was 330. So Greenwich hour angle, I'm going to show you later. Let me just type it. 330 degrees, 26.1 minute. So that is this value here under 10. Now at this moment I do not need declination, but I'm going to write it down because later on in the task I will need it, so I don't have to go back to this page. So the first value I actually read from the almanac is under 23, so the correct date, under UT time, full hour, under 10 o'clock is 330, 26.1, and declination is 12 degrees. So let me write that down. 12 degrees, 43.5. So 43.5, and I need to make a note. Is it north or south? In this case, it is north. Another thing that I need to check here is, because declination of the sun, unlike other stars, is changing every hour, I need to check what is happening to declination in the next hour. So as you can see, it goes from 43.5 to 44.3, 45.1. So that means it is changing north. So that means the correction I have, I don't know which one it is, the value of the correction, but I know that the value of correction is going to be positive, it's going to be north. And the way to get the correction is by using this D value. So on the bottom of the page, let me zoom out completely. So on the bottom of the page, where you have on the top, you have sun, you have Greenwich hour angle, one column, you have declination, second column, and on the bottom of this column you have the D value, and the D value is 0.8. D value is not the correction, it is the value that we use to get the correction, and because the 0.8 is positive, and we also see that declination is changing towards north, that means whatever correction value we read out, it's going to be positive. So 0.8 is the value how much declination is changing on average on these 3 days between each hour. Okay, so let's go back to the file to see what I have written down. So I have Greenwich hour angle of the sun. Let me put in the symbol for the sun. Let's see, do I have a symbol for the sun available? It should be, where is Wingens? Here, this is the symbol for the sun. So this is a symbol for the sun. So this is a Greenwich hour angle of the sun, and this was the declination of the sun that we read out from the tables. And also we checked declination in next hours was changing towards the north. So here we made indication that whatever number we read out here, it's going to be north. And declination was 43 degrees, 12 degrees, 43.5 minutes. And the D value is 0.8. And let me change this. This is sun, this is sun, and this is sun as well. Okay. So now that we have Greenwich hour angle and we have declination of the sun and we have the D value, we have two options. Let's move this to another page. So we have this procedure to find the correct declination, and we have procedure to get Greenwich hour angle of the sun corrected for the exact minute and second. And also we have local hour angle of the sun. Now this one can be deleted because we do not have this for the sun. Okay. And this one also can be deleted. Okay. So declination of the sun was 1243.5 north, and it's changing towards north. So let's see the correction. The correction is found in increments and correction. So let me check the time one more time. So I have 10:08:34. So 10:08:34 is my UT time. I'm going to copy it here. So and zoom it in. So with this value, with 10, I'm going to put it in red, and this is going to be in green. So with the date and 8 minutes and 34 seconds, I'm going to get this correction here. I'm going to get correction for Greenwich hour angle. And with 8 minutes, so just 8 minutes, I'm going to get correction for declination. So that means I open my almanac and I'm looking for, let's go to almanac. And I'm looking for 8 minutes. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8. And now I'm at 8. And under 8 minutes, I'm looking for second 34. 34 is here. So this, the first column is correction for sun and planets, second one is for Aries, and third one is for moon. So that means I'm looking under the first column, under 8 minutes and 34 seconds. That is my UT time. So 8 minutes, 34 seconds, it's my UT time. And the correction for hour angle is 2 degrees, 8.5 minutes. So 2 degrees, 8.5 minutes. So that is the first thing to take out from here. And the second one is the correction for the declination, and I enter this column with D value. My D value is 0.8. So every hour declination is changing by 0.8 minutes, but in period of 8 minutes, if it is changing 0.8 every hour, it actually changed by 0.1. So the change for declination is 0 degrees, 0.1 minute. And this tables I'm using, they are called increments and corrections tables. And you have every minute between 0 and 60, and you have under 1 minute, you have two tables. One table is for hour angle correction, and the second table is correction for declination and additional hour angle correction for planets and moon. Okay, so let's go back to the Word file. So this is what I have. I have this too. Let's put them here. Okay. So I have 0, 0, 0, 0, north, and this is easy. This should be easy. We don't need to use calculator for this one. So the exact declination of the sun at 10 o'clock, 8 minutes and 34 seconds is actually 12 degrees, 43.6 minutes north. So it changed by 0.1. And now we have local hour angle. Local hour angle is, so this was Greenwich hour angle at 10 o'clock. So it was 3:20. So this is the data we obtained by using the exact hour, and this is going to be what we obtained by using the minute. So it's for 08 minutes and 34 seconds. So that is the correction. That is how much Earth moved in 8 minutes and 34 seconds. It moved by 2 degrees, 8.5 minutes. Because every hour, Earth moves by 15 degrees. So in 8 minutes and 34 seconds, is actually moved by 2 degrees, 8.5 minutes. That is this value here that we got. And at the end, we will get exact Greenwich hour angle for the sun at 10 o'clock, 8 minutes and 34 hours. So 330, I can do this because it's plus. I can do this without calculator, but as I said, if you don't trust yourself with your mouth skills, don't do this by hand, do this with calculator. So 6 plus 8 is 14, so that means 34, and this is 332 degrees. So 332 degrees, 34.6 minutes, and longitude in this task is 5 degrees, and it's west, so it's negative, so I need to keep that in mind. So every time you have a west value or south value in the equation, you put it with the negative sign in front. That is how calculator knows it's actually west or east by putting the negative sign. So 332, 34.6, so 332 degrees, 34.6 minutes minus 5 degrees, 13.9, 30.9 is 327. So 327 degrees, 03.7 minutes. And that is local hour angle of sun, lower limb, exactly at this moment between our meridian and approximate meridian of the sun. So the celestial meridian of the sun. That is how far we are from one another. So that is step 3. Let's put it here. So calculate LHA of the sun. And the same rule applies for everything. Local hour angle as angle, no matter what celestial object it is measured. It is an arc of 0 to 360 degrees, cannot be less than 0 and cannot be greater than 360. Our local hour angle is 327, so it's exactly where it needs to be. It is between 0 and 360. The fourth step is correcting the height observed to get height true. Now, because this is not planet, we do not have this correction, but we do have calendar, or maybe let's put it month. So when it comes to sun has his own dip correction. That's standard because we have horizon depression. It has index error in case the sextant has an error, and it has temperature and pressure if the temperature and pressure are taken in consideration, but it also has a unique specific table correction for sun depending on the calendar month you are observing the sun. So let's input the data here. We have height observed 4622 4622.4. So 46, 22.4. Sextant error is negative 0.6. Now the calendar month. Let's check that out in PDF. PDF. Height corrections. Okay. So we have table for altitude or height correction for sun lower limb. And we have 46. So on the left side here, we have height of sextant, observed with sextant. So we are looking for 46. 46. Come on. Okay, 46 is now exactly on the bottom of your screen. And on the top we have height of eye, and height of eye was 14. So from the top of the table I enter with value 14, and from the left I enter with 46, and for 46 the value of correction is 8.5. So 8.5. So I go here, 14 from the top and 46 from the left, and the correction is 8.5. And while I'm here on the bottom of this page, I have also calendar month, so second correction in minutes. And for April, because that's the month of observation, the correction is negative minus 0.1. So it's 8.5 positive and negative minus, so 8.5 positive for the dip and negative 8.1 for the month of April. So let me put that back in the Word file. So I have month negative of 1, and the dip is positive 0.85. So those two corrections are there, and now I need to read these two corrections for temperature and pressure. So let me open the temperature and pressure correction. I should have them here. Temperature and pressure. Okay, here I have temperature and pressure. So my height is 40 something, 46 degrees. So that means I'm looking in this column here. The temperature was, how much was the temperature? Let me see the task. The temperature was 16. So the correction for temperature is 0. In the first column, it's 0. And the pressure was 1005. And I can see it here. It's not, it's cropped, but it's for 85 is 0, for 90 is 0. So for 1000 is also 0. So both corrections for temperature and for pressure are 0. So it's 0 and 0. I don't have those two. So 0, 0. So now that I have all the corrections taken out from the tables, I can correct the height. So I have 46, 22.4. I have dip 8.5. I have month negative 0.1. And I have sextant error minus 0.6. And that mathematically gives me, let's see what I have. I have two negatives, one positive. They are total 46 degrees. And 0, 0, 0, 30.1. 30.2. No, it's 0.2. 0.2. So once you put everything in calculator, you get that the height true is 46 degrees, 30.2. Now, as you can see here, the order of the corrections, if you are just going from height sextant to height true, is not important. You just summarize them all. But if you are in high school, then the order is important, because each of these summarizations, so this plus this, is a different height. So height sextant plus this is height observed, then you have observed corrected, and then you have observed final corrected, and then you have actual height true at the end. So between each of these summarization process, you have a height that has a different label. But we are looking for just height true when we're actually doing the final result. So this is the only value that we need. So the order of these errors, once you put them in, doesn't have to follow this that you see on the screen. Okay, so we have height corrected, height true. And now the next step would be, because this is sun at any moment, for the sun at any moment we are using the same two formulas as for the star. So let me just copy them. So we have this, this, and this. All of this has to be copied. Okay, copy, sun at any moment. So step 4. And step 5 would be calculate height calculated. Height calculated is height where the sun, so where the sun's supposed to be if you are actually on the given DR position. So height calculated is sine of latitude times sine of declination. And what is important to note, sometimes people make mistake, declination that you put here is this one, the corrected one, the final one, not the first one, 43.5, but 1243.6. So 12 degrees, 43.6 is what you put here in the equation. And I'm not going to explain the equation again. You have this formula, you type in the data, and you get the end result. The end result is trigonometry function belonging to this angle. Once you revert it, depending what the trigonometry function it is. So if it's sine, you go invert sinus -1. If it's cosine, you go cosine -1, and you get height calculated. Now, after that is finished, you need to calculate distance error, delta H. Distance error is difference between height true and height calculated. And that will give you error in minutes. And because 1 minute of height is equal to 1 minute of latitude, and therefore 1 minute of latitude is 1 nautical mile, every minute that you get here as an error is actually error in nautical miles between your DR position and true position. Okay, and the step 7 is calculating true azimuth of the sun. The formula is the same. Declination is the one that you calculated, the corrected one. So it was 1243.6. I will type this in later. There's no need for you to watch me type in the data. I just want to explain you the process. And once you have azimuth calculated, you need to obey the rules. So if the LHA is greater than 180, azimuth true stays as the same as azimuth calculated. So in this case, if we go back to step 3, we see that local hour angle is larger than 180, so it's greater than 180 degrees. So that means once we calculate azimuth here, it is also going to be azimuth true. So we don't have to convert it, we don't have to subtract it from 360, it is going to be actual azimuth true. And then step number 8 is plot the data on Y chart. So the azimuth, by using the azimuth and by using the delta H value, we plot the line of position on the Y chart. Sorry. Okay, so one more time, let's go back from the beginning. Procedure for sun at any moment. So sun at any moment, we have this data given to us. First step is to find the correct UT time and date. If the chronometer time is given, we add correction of chronometer error and we get UT time. If we didn't cross midnight, then the date stays the same as the date given in the task. After that, we are looking in the almanac for the correct date page. Every page will have 3 dates on it. So once we find the correct date page, we need to find that specific date. In this situation, for 23 of April, it was the bottom date on the bottom of the almanac. And on that page, under 2304, 10 o'clock, we read Greenwich hour angle of the sun and declination of the sun. And we also make a note how the declination is changing in the next hour. So declination in next hour is increasing towards north. So that means the correction for declination is also north. So after that, we went to increments and corrections tables, and with the value of 8 minutes and 34 seconds, we took this value here, 2 degrees, 8.5 minutes, and with the information that the declination is changing every hour by 0.8, we read out that for 8 minutes, correction is 0.1. After we applied these two corrections, one correction for declination and we added the correction for Greenwich hour angle, we added our longitude that was negative because it's west, and we have local hour angle. So one more time, local hour angle is how far our meridian is from apparent meridian of the sun at that moment that we are looking at the sun. Step number 4 will be to correct height observed to get height true. We have a couple of corrections. One correction is for sextant error. If it's given to us, we include it in calculation. Then we have correction for horizon dip and specific table correction for sun that is depending on the month of the observation. And then we have temperature and pressure. Depending are they negative or positive, we just summarize all this data to get height true. And after that, by using two formulas, we calculate height and we calculate azimuth. So sine of height calculated to give us height calculated, and azimuth true by using the cosine formula. Distance error is obtained by subtracting height true and height calculated in this order. If the result is negative, that means that we are actually further away from the our true position is further away from the DR position, and if we get a positive result, that means our true position is closer to the sun from our DR position. And then the step 8 would be plot the data on the Y chart. So this is something I'm going to do last, because plotting on the Y chart is practically the same for all the stars and planets. And then you have something specific for sun. So sun has one method and the second method depending when we observe the sun. And because of that, I'm going to put that everything in one video after we collect all the data. So that was sun at any moment. And now we have sun at noon. When we are observing sun at noon, the procedure is no longer the same. We have something specific when it comes to that. Let me just get the data. So let me copy the data from here. Copy. So sun at noon. So in sun lower limb, in moment of meridian passage. Let me delete all of this. So observer is observing sun lower limb in moment of meridian passage at 23 of April, and assumed position is 46, 17.6 and 530.9. Okay, so now the position has changed. Okay. And the height is, let me see how much is the height. Height is 56, 52, 53, exactly 53. Okay. And the time of observation is at meridian passage. So when you have sun at noon or in meridian, you don't actually get the time of observation. You have to calculate the time observation. So the correct procedure when you want to observe the sun at noon in meridian is that you enter the almanach and you look at what time you need to go outside and actually measure the height of the sun. So the first step, so this information here is actually obtained after you perform the first step. So the first step is to find the correct UT time, and date is not important because it's middle of the day, so unless you are exactly on date line, the date is going to be the same. So how to find the correct UT time? So the correct UT time of when you need to observe the sun is calculated actually by using this pattern. So let me write it down. Let me copy this. So I have a backup. Okay. So the first thing you need is meridian passage. So mer pass or TM. No, not trademark. TM. Let me move that aside so you can see it. So meridian passage TM, and we subtract that minus longitude. So what is TM meridian passage? Meridian passage is the actual time of noon for a person in Greenwich meridian, so 0 meridian. This value here is actually obtained from almanach. So we have to go back to almanach. Let's open it up. Almanach. So when you open almanach on the page of the date that you need and for the sun, so you have sun and the moon on that page. If you look at the bottom right corner, let me zoom that in. So on the bottom right corner, okay, so bottom right corner, let me screenshot this so we can use it and put it in here. Okay, let's go back to Word file. So here on the bottom right corner of the page where you have sun and moon, you have the information for every day of those 3 days, and then you have something that is called equation of time, and then you have meridian passage. The equation of time is the exact difference in minutes and seconds between the true noon and the celestial or human noon, the civil noon, and midnight as well. So that means between true noon and human noon, the error is 1 minute and 45 seconds for date 23 of April. And meridian passage is going to happen at 11:58. So when the human clock is showing 11:58, it is the actual moment of noon. It is the actual celestial astronomical noon. So when the human clock is showing 11:58, the solar clock is showing 12:00. So that is the moment of meridian passage, and that is what we put here. So we put 11:58:00. So that is the time of meridian passage for person who is exactly on Greenwich meridian. I'm not on Greenwich meridian. I'm actually a little bit to the west. So that means I need to convert my longitude into time. I need to calculate how long in minutes I am from the Greenwich meridian. And in order to do that, I have my longitude, 5 degrees. So let me put that in calculator, and it's west, so it's negative. 5 degrees, 30.9. So this is the value of my longitude expressed in angle. I need to know how much this is in hours. So in hours and minutes in value of time. So how long does it take Earth to move by 5 degrees, 30.9 minutes? I get that by dividing this value with 15. So longitude divided with 15 that is how I convert angle into time. And it is actually negative 0 hours, 22 minutes and 4 seconds. So let me put that in. So negative 0 hours, 22 minutes and 4 seconds. Now, because I'm west, so that means 11:58 minus the answer. That means when I'm looking at the sun and it's noon for me, for my position, for my meridian 5 degrees west, the actual time in Greenwich meridian is going to be 12 o'clock 20:04. So I have noon, and in that exact moment when I have noon, the person in Greenwich has 12 hours, 20 minutes and 4 seconds. Now, this is a part that is tricky, that people get confused all the time. So let me get that as well. If I'm using my clock, ship's clock, and my ship's clock, not chronometer clock. Don't confuse ship's clock from chronometer clock. Chronometer clock is always pointing towards UT time, and it has slight error, minor error in minutes. The ship's clock is a clock that is showing the time in the time zone ship currently is. So in order to get the exact local time, so local time TX of that time zone, what I need to do is I need to add the time zone of my location, so plus X. Now, how do we get the time zone of our location? In order to obtain time zone of our location, we need to divide our longitude with 15 degrees. But because we are not looking for astronomical distance, we are looking for economical distance between our position and Greenwich meridian, we round that value up. So this value here, 0:22 minutes 04, it's actually 0 time zone. If it was 0 hours 36 minutes, that would already be +1. So that means we would be in +1 time zone. So let's review that. If the person is at 60 degrees east or west divided by 15, the time zone is 0. You see, 0.4, 0.3, 0.2, 0.1, all those numbers, when you round them up, they get 0, they give you 0. But if the person was 8 degrees east or west from Greenwich, 8 divided with 15 is 0.53. So if you want to round 0.53, it's actually 1. So person that is 8 degrees east or west from Greenwich is actually in the time zone minus or +1. So that is how you get time zone. So here, where it says longitude, you divide longitude with 15 and you do not round that value up. You keep it the way it is. And when you are calculating time zone, you get the time zone in the same manner. You divide longitude with 15, but you round that number up because you are looking for economical time zone. So in this case, the local time, because I'm in time zone 0, is actually the same as the Greenwich time is 12:20:04. So if you look at here, just because I'm west from Greenwich, it means that if I want to observe the sun at noon, I can do that by going outside around 12:20. So my human clock is showing 12:20, but I can still observe sun at noon. In case I was on east side, or if it was a different time of a year, for example, if let's say, let's go to almanach 76, let's go 200. So let me show you something interesting that happens. Let's switch to PDF. So you see here, I picked what is this? What is this? This is October. So in October, meridian passage happens at 11:44. So that means if you are east from Greenwich, and if you want to observe sun at 12 o'clock and you go outside around 12 o'clock, you're already going to be too late, because the noon is already going to pass. So that is one of the reasons why we calculate the time of observation before we actually do the observation, because we need to know when we need to go outside. Half of the year, if you go outside around 12 o'clock, you still have 15 minutes, because in the next 15 minutes the sun is going to be in your meridian. But the other half of the year, sun actually comes earlier in the meridian. So if you go outside at 12 o'clock that your human clock is showing, the noon has already passed. It's been, as you can see here, almost 15-16 minutes already the actual true noon. So that is the reason why first we need to check at what time we're going to go outside and read the height of the sun. So once we have this, once we know the time, let's go back. So once we know the time of observation, what we actually do is, around this hour and minute, we go outside and we measure the height of the sun. And if the height is changing, we are waiting until it stops rising. So you will have, when you observe the sun and you want to read the height at a point of meridian, the height of the sun is going to rise, and then at certain moment it's going to start to fall, because actually sun has crossed the meridian. And just that value that you measured before the sun started to decrease in height, that is the height of culmination, that is the height at meridian passage. So it's different from sun at any moment. When you are measuring sun at any moment, you just go outside and you measure the height of the sun, and that's it, finished. But when you want to measure sun at noon, you actually have to go outside and monitor how the height of the sun is changing. If it's rising, you do not count those heights until the height starts to drop. When the height starts to drop, the last height before that height that you actually read, that is the height of culmination, that is the height, maximum height of the sun in the moment of crossing your meridian. So that is different procedure when it comes to reading the height of the sun at any moment from the reading the sun height at noon. So you have to monitor the sun a little bit longer before you can actually say, aha, this is the height, culmination height for meridian passage. So after you have that, after you have correct UT time, what you do with this time is delete this, cut. Now you are already on the correct date of the almanac, so find the correct date page in almanac and read the declination of the sun. So let me copy this procedure from the last task. Okay, this is what we need. We need declination of the sun. We are still on the same page, 23 of April, so D value is still 0.8, but declination is not the same. So let's read out the declination. Declination of the sun, 76. Let's go back to PDF file. So we are looking on the date of 23 of April, so this is 21, I need to go down, 23 of April at 12 o'clock. So at 12 o'clock, not Greenwich hour angle, we don't need Greenwich hour angle, we are looking for declination. So declination at 12 o'clock is 12:45.1. So 12 degrees, 45.1 north. And we already know, but we can also double check, it's changing north in the next hour. and the D value is still 0.8. Now the minute of UT time is 20, so that means I need to go under 20 minutes, 10, 12, 16, 18, 20. And 20 minutes, the seconds are not important because I'm looking for a correction for declination. And the D value is 0.8, so for 20 minutes and 0.8 of D value, the correction is 0.3. So let me grab a screenshot of this. Okay. And put it in the book. Okay, let's go back to Word file. This is too large, it doesn't have to be this big. So D value is 0.8, under 20 minutes, correction is 0.3. So the correction is 0 degrees, 0.3 minutes north. And because it's changing towards north, that means I can just summarize these two values. 45.4 minutes still north. So it changed by 0.3 minutes northwise. So that is the correct declination of the sun at that moment of noon observation. And now we do not calculate local hour angle. When we are calculating sun at noon, we do not need LHA because LHA is 0, if you can comprehend this. If the sun is in our meridian, that is the moment of noon. And if it is in our meridian, the local hour angle between us and the sun is 0. So it doesn't exist. It exists, but it's just 0. So we have this local hour angle. We can delete all of this. And this is not the procedure for the sun. Calculate. Okay, so the next step is, did we correct the height? We didn't correct the height, so the next step is correcting the height. Let's flip this up. So the step number 3 is correcting the height. X. So correcting the height observed to get height true. Let me copy the procedure because this is the sun. So it's the same procedure as before to get the correct height. Let me pause this and delete this. Delete rows. Okay. So height measured with sextant was, how much was the height? It was 50 something. Let's see. 56.53. Okay. So 56.53.0. Sextant error is the same, month error is the same because it's April, and we need to read out the dip for 56. Do I have table for the sun? I didn't took the table for the sun. So we go to the height correction for sun and planets. We go to this table and we are looking for 14 meters. So the top is 14, so this one here. And the height is 56. So for the height of 56 observed with sextant and 14 meters height of eye, the correction is 8.8. So 8.8 is the correction. So one more time, you enter this table from the left with height observed with sextant and from the top with height of eye, and where those two values intersect, that is your correction. And if it's if there is no sign in front, it's positive. If there is negative sign, it's negative. So 8.8. Temperature and pressure are 0, so we don't have to look for that. And the final correction is this is -7, this is 8, so it should be 56, 53.7, 56, 50, 50, 50, 50 minus plus 8. Oh, we are crossing. Let's do this with calculator. So 50 degrees, 53 minutes, plus 8 degrees, 8.8 minutes, minus 0 degrees, 0.7. 57, 1.1. 57, 01.1. That is height true. And now the pattern for layout, let's put one not above. I need one above. Okay, and let's delete this too. There is something unique when it comes to sun at noon. Sun at noon, unlike observation at any other moment, doesn't give us delta H value. It gives us automatically our latitude. And the procedure is we start with 90 degrees and we subtract 90 degrees from the height true. This will give us zenith distance. Now, what is zenith distance? If you can recall from the first lecture when we draw celestial sphere, we have our horizon level and we have the point that is directly above our head. That point is called zenith, and the distance between horizon and object is called height. And the leftover is 90 degrees minus height. And that leftover is also zenith distance. So that is how far the object is from our zenith. So if we subtract 90 degrees and height true, we are going to get ZD, and ZD is actually zenith distance. Zenith distance. And now, because the sun, and this is only for sun in the exact moment of culmination when it's in our meridian, because of that, if we add or subtract declination, how far is the sun from the equator to the zenith distance, ZD, we actually going to get, let me delete this, delete the row, we're going to get our latitude of meridian passage of MP. So we directly get our latitude. So latitude of meridian passage. This is declination. Declination of the sun. And this is zenith distance, and this is height true. So height true is 57 or 1.1, and that means zenith distance is, let me subtract that, so 90 degrees minus 57, 1.1 is 32 degrees, 58.9 minutes. So that's a zenith distance. Declination of the sun was 1245.4. So 1245.4. And now, because it's north, we need to add it, so plus 12 degrees, 45.4. And our actual latitude is 45 degrees, 44.3 minutes north, because it's positive. And this is our actual latitude. This is our latitude of meridian passage. We can plot it directly on white chart as a straight line, straight parallel line on the white chart. So that is the step 4 here. So when you are observing sun at noon, the procedure is shorter because you do not have to calculate local hour angle because local hour angle is 0. So we have, one more time, sun at noon. We have the date, we have assumed position, we have data from the observation, so height of the eye and sextant error. We have ship's chronometer error, we can have temperature and pressure, and the height observed with sextant is given to us. Time of observation is not given because that is the time of meridian passage. So the first thing that we need to do is find the correct UT time. We do that by, in the bottom right corner of almanac, we look for the exact time of meridian passage. This is human time of meridian passage for Greenwich meridian. And we need to convert that into our time by dividing our longitude with 15 to find out at what time at Greenwich we are going to have at our position on our location exact noon. So when the Greenwich has 12:20, we will have the actual noon. That will be our noon, our 12:00 celestial 0. That is the moment when the sun is going to be in our meridian. So around 12:20, we actually measured this height. When it stopped rising, we measured it to be 56 degrees 53 minutes. And then we read the correct declination from the almanac for that 12 hours and 20 minutes. So this is declination. Do I have, let me put layout inside, right? So this is declination at 12:00. Okay. And this is correction for 20 minutes. Correction for 20 minutes. And this is declination exactly at 12:20:04. So that is what we have calculated here. This was declination at 12 o'clock. We read from the increments and correction tables by how much Earth has moved in 20 minutes. So if it's changing 0.8 every hour, it actually moved 0.3 in 20 minutes. And we have declination exactly at 12:20:04. Once we have that declination, we correct the height observed to get the height true by using the tables for the sun. And once we have the height true, we calculate latitude of meridian passage by subtracting height true from 90 degrees to get zenith distance. That is how far our sun is from our zenith. And then when we add or subtract declination, add if it's north, subtract if it's south, we get our actual latitude. We get how far we are from the equator. So zenith is how far we are from the sun. Our zenith is how far the zenith is from the sun. Declination is how far the sun is from the equator. And when we add those two numbers up, we get how far we are from the equator because we are observing the sun when it's exactly in our meridian. So this procedure is only valid for observation of sun at noon. Now, hoping that this is clear, we go to another procedure that is also unique, and that is the moment of sun. We are measuring sun in the moment of sunrise and sunset. So let me get the data for sunset and sunrise. Okay, so the date is 26th of June. In moment of sunrise, let's do sunset. And the assumed position is 41 degrees north and longitude is 83 degrees north. We do not need this. Height of eye is also not important. This is not important. None of this is important. This is also, we do not need this as well. What we need is azimuth. So azimuth compass. So azimuth compass. Let me insert the symbol for azimuth. Azimuth C compass is 303 degrees. Variation is 1 degree, 12 minutes west. Annual change is 6 minutes east. And declination is what we are looking for. So observer is observing sun lower limb in moment of sunset at 26th of June. And the latitude is 41 degrees north, longitude is 83 degrees west, and we measured from our azimuth magnetic compass that the value of azimuth of the sun is 303 degrees. What we actually want to check is what is the declination of this compass, what is the error he has, and from the chart, and let me put, this is obtained from nautical chart. So this is from the chart. This is obtained from magnetic compass. Okay. And we want to calculate declination of this compass. So the first step, is find the time of sunset. Find the time of sunset. So in order to find the time, find the time of sunset, we have to go in our almanac and find 26th of June. So let me prepare that. 26th of June should be around page 100 or something. 140. Let's try 140. 140 is July. Okay, then 120 should be June. Yes. Okay, let me switch to PDF so you can see what I'm doing. So I have 26th of June, and this is the page for the sun. Let me zoom out. So this is the page for the sun on 26th of June, and I'm not looking at this left side of the page at the moment. I'm only focusing on the right side of the page, because on the right side I have something interesting. I have, for every latitude between 72 degrees north and 62 degrees south, I have time nautical civil of twilight and time of sunrise. And on the bottom here, under the sunrise, I have time of sunset. So what I do now is I go to the sunset section. Sunset section, you see here sunset, and I enter with my latitude, and my latitude is 41 degrees north. Now for 41 degrees you could interpolate the data from the almanac, because you have for 40 you have 1933, and for 45 you have 1955. So if the task is asking for you to be precise, then you have to do this. Then you have to write down the both datas and actually interpolate the data for your time. So I'm just going to copy the data from the table for the first value of latitude that is under my value, and the first value that is above my value. So the first value that is under my value is 40 degrees. And the first value that is above my value of latitude is 45 degrees, because my latitude is 41. So I'm taking 40 and 45. The time of sunset for 40 is 1933, and for 45 is 1951. Okay, so that is the data I got here. So you go in under latitude, under sunset. So let's go back to the file. So this is what I have now. I have that for 40 degrees, the time of sunset is 1933. For 45 is 1951. And this is what I need. I need what is the time for 41. So the procedure goes. So in order to get time of sunset for 41 degrees equals, and let me put this in the table because I'm actually going to type a formula. Merge. Okay. Let me center this. Okay. So the time of sunset for 41 is actually, so the formula goes like this. My value, so my value is 41, minus the first value that is under my value. So the first value that is under my value is the value above 41, that's 40. So 41 degrees minus 40 degrees. And then on the bottom, 45 degrees. So the value that is above my value, the first value above my value, minus the first value that is under my value. So my value, 41, minus first smaller under mine, and this divided by 45 minus 40. So the value that are present in the table, first larger than mine and first smaller than mine. Okay, and let me put now another here and merge, and then like this. Now this is multiplied with, now once I have that, the formula continues. I need to subtract the value that belongs to the number that is higher than mine, so 1951 minus 1933. So come on, and all of that plus the last number. So I'm going to walk you through this formula. This is the formula for interpolation of the data from the table. This is not the formula for celestial navigation. This is the formula for interpolation that is used every time you have a table and you want to extract the numbers, but you do not have the exact numbers for the values you are entering the table with. So in our case, we have the time of sunset for latitude of 41. So let me mark that with green. So that is green here, green value. And then we have the parameter, we have our own latitude, and we have the first latitude that is under us, so that's 40 degrees. And then we have the first latitude that is above us, and let's put it in blue, so that's this one, blue. We need to get this because this is actual percentage, how much our time in percentage is different for the time that belongs to 40 degrees. So that belongs to the time that is first latitude under our latitude. And we need to multiply that with the difference between these two values. So the difference between these two values is actually 100%. So for 40 degrees, this is 0%. This is 1933. For 45 degrees, this is 100% of error, 1951. I need to find out how much the time changes for 1 degree. So basically, I have 1951 minus 1933. That is how much the time can change maximum between the 5 degrees. And then that number multiplied with percentage of change will give me the percentage of change from the first value for 40 degrees. And then I summarize that to that value, and I get, let's put that in calculator, so 41 minus 40 divided with 45 minus 40 times 19 o'clock 51 minutes minus 19 o'clock 33 minutes plus, I repeat the last number, 1933. And that is, so the time of sunset is actually 19, it's time, so 36. So this is the actual time of sunset for a person at 41 degrees latitude. So basically what we did is, this time here is how much? Let's see, 51 minus 33 is 18 minutes. So in span of 5 degrees, the time changes 18 minutes. So if we divide 18 by 5, that means for every degree, the time is changing by 3 minutes and 36 seconds. So one more time. In period of 5 degrees, the time is different by 18 minutes. So 18 minutes in 5 degrees. So that means time is going to change for every degree by 3 minutes and 36 seconds. Because our degree is just 1 degree above 0. So that means on this time, we just add 3 minutes and 36 seconds. And the end result is 19:36:36. That is the actual time of sunset for latitude of 41 degree. If you want me to explain interpolation of the data from the table, I can do that in a separate video, because this is the procedure that we use for every table. Instability, in terrestrial navigation, in celestial navigation, in any operations where you have to extract the data from the table. So this mathematical procedure that you see here, this is not celestial navigation. I repeat that one more time. It's not a celestial navigation. This is how you interpolate data from the tables. So it goes my value minus lower value divided with higher value minus the lower value multiplied with the value that belongs to the higher value minus the value that belongs to the under value of mine, all of that plus the value that belongs to the value that is under my value. So that is table. It doesn't matter that it says here degrees or time. No matter what numbers are here, we have 5 numbers. We have one number belonging to one data and one number belonging to one data, and our number is between those two values. So that means we need to interpolate between those two values to get the value belonging to our data. Okay? And now that we have the exact time of sunset for 41 degrees, the next step is to get declination of the sun. And I have procedure for declination of the sun, so let me just copy it. So let me copy this, remove all of this. Also, this is not important. We do not have this. Delete rows, home, no border, and border here. So we need to read the declination at 19 o'clock for this date. Date is 2020, what's the date? 26th of June. So let me show you what I'm doing in Almanach. I'm searching for 26th of June. And I'm not calculating Greenwich hour angle or local hour angle. I don't need that. I just need declination. So I need declination at 19 o'clock. Declination at 19 is 23 degrees. So 23 degrees. and 19.5. 19.5, and it's north. Now, I need to observe what is happening to declination in the next hour. In the next hour, declination is decreasing, so that means the correction is south. So let me put that declination is north, but the hourly change is south, so it's changing towards the south. On the bottom of the page, I have the D value, and the D value is 0.1. So 0.1. And now I need to go to increments and corrections. The minute of observation of the sunset is 36. So I need to go under 36 minutes. And the correction for D value of 0.1 is 0.1. You see here for 36 minutes. For D 0.1, correction is 0.1. So let's go back to the Word file. I have declination of the sun 2319.5. Correction is 0.1 in south, so that means the total declination is 23 degrees 19.4. So it's still north, just 0.1 minute less. And then we have not this for sure, and not this for sure. Let me delete all of this. Come on. So the next step is calculate azimuth true of the sun at moment of sunset. Now, there is something specific when it comes to sun in the moment of sunset, and that is that the bearing can be calculated by simple formula. Let's put it here, simple formula. So cosine of azimuth calculated, insert symbol azimuth calculated, equals to sine of declination divided with cosine of latitude, and that's it. So that's the entire formula. That is how you calculate azimuth of the sun in the moment of sunset or sunrise. So it's the same formula for both options. Let me put the line here and let me center this. Okay, so we have sine of declination divided with cosine of latitude. So let me put that in calculator. Declination is, so sine of declination is 23 degrees 19.5 divided with cosine of latitude, and latitude is 41, so 41 degree. So we have 0.524, shift cosine to reverse. So azimuth calculated, is 58.4 degree. It's an angle, so we have to round it up to 1 degree. Now this is azimuth calculated. We have the rules. So rules, azimuth calculated is equal to azimuth true for sunrise, but azimuth true is 360 degrees minus azimuth calculated for sunset. And this rule is a result of the fact that cosine as a value cannot give us number above 180 degrees. So in our case, cosine value gave us 58.4. that is not the moment of sunrise, that is actually angle, that is not the angle of sunset, it's the angle of sunrise for that latitude. So we need to subtract the value from 360 to get the angle of sunset, and that is azimuth true is actually 301°.6. So that's the value of azimuth in the moment of sunset. If we were calculating sunrise, this would be the azimuth true. It will remain the same, but because we are at sunset, we have to correct it by subtracting it from 360. So once we have that, we need to get variation for year of the task. We have variation from the chart, and let's put it 2000. So variation in 2000 was 1 degree 12 minutes west. Annual change is 6 minutes. We need variation for 2008. That's the date of the task. So instead of west, I put that it's negative. Instead of east, I put it's positive, so 0 degrees, 6 minutes. And this is the annual change, so that means I need to multiply with number of years between 2000 and 2008. That's 8 years. And because it's positive, it's plus. So let's see, I have negative 1 degree, 12 minutes. And 6 times 8 is plus 0 degrees, 48 minutes. And how much is this? So this is negative 12 and 12, 0 degrees, 24 minutes. Let me check. So negative 1, 12 plus 0, 48 equals, oh, I forgot the bubble. Yes, it's negative 24, so that means it's west. We can also, because we are looking for angle, we can also convert that into degree, so that's negative 0.4 degree. So that's variation. And now we are looking for, did I put, no, it's not declination, it's deviation. It's deviation. And deviation is, the formula for deviation is azimuth true minus azimuth compass minus positive or negative variation. Now, if you are not using the formulas, if you are using that pattern where you have T, MC, and then in between, you can also do that. I prefer formula. So azimuth true is 301.6 degree minus azimuth compass, that is how much we read from the compass, is 303 degrees minus variation, that is negative, so minus 0.4 degree. So 301.6 minus 303 minus 0.4, and deviation is minus 1 degree. Let me put this on the next page. So let's go back. So the procedure to get sun at sunrise or sunset is very simple, very short. We are looking for deviation of our magnetic compass. We have observed the sun lower limb in the moment of sunset. We have our latitude. As you can see, longitude is not important. We never use the longitude value here. We have variation from the chart, and we need to read the deviation of our compass. The first step was to find the time of sunset by using our latitude. If our latitude is not directly in the table, so if our latitude was 40 or 45, we would just read this. If our latitude is not directly available in the almanac, we need to interpolate. You do not have to do this by using formula. You can use your own mathematical knowledge. If from here to here is 5 and from here to here is 18, that means for every 1 it's changing by 3.5 minutes, because the declination is not going to change drastically between 5 and 6 and 18 minutes for the sun. So it's not really extremely important that you be precise here, that you have to actually use the formula to interpolate. But if you don't know how to interpolate the data between two values, like I said yesterday, if you have problem between finding the middle and quarter between the two values, so what's the middle between 1 and 1.6? The middle is 1.3. What is 3/4 between 1 and 1.6? It's 1.5. Because 1/4 is 1.1, and then you have 1.2, 1.3 is the middle, 1.4 is second quarter, third quarter, and then the last one is 1.5 before you reach 1.6. So it's just mathematical in your head interpolation of the data. Once we have the time of sunset, we enter the page in Almanac with correct date and read out the declination and D value. So declination for 19 o'clock was 2319.5. The D value is 0.1. With 36 minutes we entered and we checked that the change is 0.1. Because it's changing towards the south, we actually subtracted this value. It was negative. And then we have this short formula to calculate azimuth of the sun. And the azimuth that we obtain is azimuth calculated. The rules state that if the moment of observation is actually sunrise, azimuth true is equal to azimuth calculated. But if we are observing sun at sunset, we need to subtract whatever we have calculated by 360 to get the actual value. Once we have that, we correct the variation for the year of the task, and then we put all of that in formula for deviation. So that's a step 5. Step 5, calculating deviation of magnetic compass. And that's it when it comes to sun. You have sun at any moment, you have sun at noon, and you have sun in the moment of sunrise and sunset. Those are the 3 options for observing the sun. The first option, sun at any moment, is used to find your position. So we do this when we want to find the position of observation. Sun at noon is when we want to calculate our latitude of our position, because the sun at noon gives us directly our latitude. So once again, that's our position. And then when we are measuring sun at sunrise or sunset, usually it is to get deviation of our magnetic compass. And those are the procedures for sun at any moment. If you have any questions about this, ask me in the comments or send me a message later on. And the procedure for Polaris and procedure for unknown celestial objects are quite long, and we already are 1 hour and 40 minutes in, so that is something I'm going to do tomorrow. So I'm just going to do sun today and keep it as such. So sun at any moment procedure, sun at noon, and sun at sunrise. Once I finish and I complete all of this, once I decorate this document, it's going to be available on my web page. If you are candidate of the training centers I work for, you will get this once you apply to some of the courses that have celestial navigation. And you can also purchase this by going on my site and to my publisher. You can also purchase this textbook. It's going to be available, I believe, next month, so in maybe 10-20 days. Okay, thank you very much for everyone who's been listening. If anyone is listening, let's see, do we have some people on board? No, we don't have anybody. That's it. Talk to you tomorrow, 10 o'clock, same time. We continue with Polaris, an unknown celestial object. This was sun observation at any moment at noon and sunrise, sunset.